So that process is pretty intense, so I want to show you another one. So this is another situation where we have an expression with x in the base and another expression of x in the exponent. But if we try to evaluate this limit to infinity, on the base we get 1 plus 0, which is just 1, raised to the infinity. So this is 1 raised to the infinity. So this is another indeterminate form that is not L'Hopital ready. But just like before, since we have a, sorry, this guy's not focusing. Since we have an x to the base raised to an x, we can use natural logs again. So we're going to start off assuming that this fact does have an answer, and that it's L. So now I can say, well, the natural log, or the limit, excuse me, of as x goes to infinity of the natural log of 1 plus 3 over x raised to the 5x equals the natural log of L. So once again, I'm going to work with the left side here and simplify it down. So the properties of limits say, well, I can grab that 5x and pull it down front. If I try to look at the limit here, well, I'm getting infinity times infinity, because the natural log of 1, or actually infinity times 0. This is going to go to infinity, and this is going to go to the natural log of 1, which is 0. So I'm still in an indeterminate form, right? So I have to keep working. I'm not ready for L'Hopital yet. So just like before, where I took that square root and moved it into the denominator, I can move this 5x into the denominator, but I can't just put 5x in the denominator. I have to make sure it's an equivalent expression to this. So I can say, well, I'm going to leave the natural log of x up here, and I'm going to write this as 1 over 5x. So now we can see that if I multiply this by the reciprocal of this, the 5x ends up back in the numerator where it belongs. So this is equivalent. Now if we look at this, ln of 1 is 0, the limit of the denominator is 0. Now I've got it L'Hopital ready. I'm in an infinity over infinity situation. So now we're going to take the derivative of this, so the derivative of the numerator, because this is a natural log, is 1 over this stuff. So my 1 plus 3 over x is here, and then we multiply that expression by the derivative of the stuff inside. So the derivative of 3 over x is negative 3 over x squared. So that's just a power rule. 3 times x to the negative 1, that's where the negative 3 comes from, minus 2. And so I'm just writing it in a fraction form so I can hopefully simplify. That's the numerator. The derivative of the denominator is going to be, this is the same thing as saying 1/5 x to the negative 1. So I get negative 1 over 5 x squared, because it's negative 1 times 1/5 x to the minus 2. So now, if I go to simplify this, I'm going to say, well, my first fraction, the one in the numerator, is this guy. So notice here, because numerators and denominators matter so much, see how I drew a big long fraction bar to indicate the numerator from the denominator, and then when I got down here, I drew a nice big long fraction bar, so all of this belonged in the numerator and all of this belongs in the denominator. So when I go to do this step, right, I'm multiplying by the reciprocal of this, so this is the guy that gets multiplied by 5x squared, right? And there's my negative 1. If I look at this guy, right, if I want to clean it up, I can't just say, well, actually, I need to get a common denominator down here. So I'm going to go one more step out, and I'm going to say, let's leave the negative 3 over x squared. And here, I'm going to get a common denominator. So I'm going to multiply this 1 by x over x. So I get x plus 3 all over x times 5x squared over negative 1. So now what I have is a fraction divided by a fraction times this other fraction. So I'm going to deal with these two. So I can take this fraction and then multiply by the reciprocal of this fraction. So I get negative 3 over x squared times x over x plus 3, and then we still have our 5x squared over negative 1. So now I can see if I can clean this up just a smidge. So this x squared is going to cancel this x squared. This negative is going to cancel this negative sign. And so all I'm left with, if I multiply across the numerator, is 3 times 5 times x, so I have 15x in the numerator. And then I just have x plus 3 in the denominator. So this is still an infinity over infinity situation. But it's a much, much easier one to work with. So that means I can apply L'Hopital again. And I can say, well, the derivative of the numerator is 15 over the derivative of the denominator, so this limit is 15. But that is just the result of the left side of the limit. So, just like before, 15 equals the natural log of L. So if I raise each side over e, I get that the limit of all of this was really e to the 15th.